All right, welcome. Today, we're diving into something critical. It's a problem of late-night gastronomy, a real challenge of engineering and structural integrity that, let's be honest, affects millions of us. We're talking about Project Midnight Architect.
So, let me ask you this. You've been there, right? It's late, you're in the kitchen, you've gathered all the components, you know exactly what you want to build, and yet, total disaster. Are your late night snacks suffering from what we can only call structural failure?
Well, believe it or not, this phenomenon actually has a clinical name. It's called condiment slippage syndrome, CSS for short. And yeah, the official definition is a messy, discouraging experience resulting from a failure to synthesize sandwich components into a stable structure. Look, this isn't just about a mess. We're talking about a complete systems failure.
Okay, so Section 1, a crisis of construction. We're going to start by looking at the specific high-risk environment where these failures happen most often. We call it the high-stakes snacking window.
You know, data shows that adult learners, and yep, that means you and me, we frequently experience what experts call performance failure. And it happens during a really specific window, the critical hours between 11 p.m. and 2 a.m. This is not a coincidence, people. It is a predictable pattern of systemic collapse.
And the consequences? Oh, they're significant. We're not just talking about, a dropped tomato here. Condiment slippage syndrome, it leads to measurable cognitive frustration, a huge increase in physical cleanup time, and, let's face it, a deeply discouraging culinary experience. It can totally ruin your morale.
But look, we're not just here to diagnose the problem, we are here to present the solution. And that brings us to Section 2, the Velcro method, a proprietary assembly strategy.
Now, the main goal of this method isn't really about flavor or how pretty the sandwich looks. Nope, it's all about physics. The Velcro method is a fully engineered process designed for one thing: to maximize the friction coefficient between all the sandwich layers.
All right, Section 3, the 3 critical layers. To really get this method, we have to do an architectural breakdown of the 3 key layers that make up the whole system. So it's a step-by-step, 3-part process. Simple. You start with the foundation layer, then you move to the barrier layer, and you finish with the most crucial component of all, the friction layer. Every single one has a specific, absolutely vital job to do. Okay, let's get into the material science here, because it's crucial. First, your foundation. That's a high-density carb, like sourdough, and its job is to provide that solid, structural rigidity. Next up is the barrier. Think a fat-based spread like mayo or butter. It adds flavor, for sure, but it also introduces risk. It can create a lubrication zone. And that brings us to the real innovation, the friction layer. This is where you use textured greens like kale or romaine to create what is essentially a micro-interlocking system.
And right here, this is the most common point of failure. Look at the left. That's the incorrect way. You put a lubricant, mayo, right up against a high-moisture vegetable like a tomato. What happens? You've just created a slippage plane. The whole project is doomed before you even start. Now, look at the right, the correct way. You put those textured greens against your load-bearing protein, the meat or tofu. That creates grip. It prevents any lateral movement. Game changer. Okay, Section 4, the science of sandwich grip. I mean, building one successful prototype is great, but how do you make sure it's a repeatable success? Well, that requires some proven pedagogical strategies. So to make sure you actually retain this knowledge, the method uses established principles from instructional design. For example, we use Mayer's signaling principle in the blueprints, the visuals, to highlight what's absolutely critical. We also use the contiguity principle, which just means putting labels right next to the graphics to reduce your cognitive load. But the most important one is safe failure modeling.
And this is the key, right? Safe failure modeling. It's really all about understanding why things go wrong. If you can analyze the physics of a sliding tomato, you can be empowered to, proactively engineer a solution. You can prevent that catastrophic failure before it even has a chance to happen. It's a proactive approach, not a reactive one.
All right, that brings us to Section 5, the final gravity test, because theory is great, but it has to be validated by practice. This is the final summative assessment. The test protocol, it's simple, but it is absolutely rigorous. Parameter number 1, your final creation must be held at a perfect 90-degree angle to the plate. No compromises, no tilting, 90 degrees.
And the second parameter, it's even more demanding.
The success criterion is a 0% ingredient drop rate. I'm serious. Not a single shred of lettuce. Not one crumb. Absolutely nothing can fall.
Only a sustained 0% drop rate, held for at least 5 seconds, only that constitutes mastery of the Velcro method. It's the ultimate validation of your engineering skills. It is perfection.
And that brings us to our final thought for today. By applying all these principles, physics, engineering, instructional design, to a simple midnight snack, have we finally perfected the sandwich? Or have we just begun to truly engineer our food? That is definitely something to chew on.